So I think it's time. So Sagar, you're muted, but you tell me when we should start.
Yeah, you can start now.
Hello, everybody. Welcome to the third edition of our QuantTap seminar, Quantum Computation for High Energy Physics. It's an immense pleasure to welcome Professor Ignacio Cirac today from the Max Planck Institute for Quantum Optics. Ignacio has been one of the pioneers and founders of quantum information science and quantum computation, in particular for his proposals of how to implement quantum gates and also how to use cold atom systems to do quantum simulation, as well as his understanding on entanglement, matrix product states, continuous variables, quantum information, etc. I think the list of achievements is too long to be listed here. Is just one of the pioneers and leaders and of the field of quantum information. It wouldn't be the same without him. And so it's a great honor to have Ignacio today with us to tell us also about how to use quantum information to investigate quantum field theory. So thank you very much, Ignacio, for participating in our QuantTap seminar, and the floor is yours. Thank you.
Okay, thank you very much, sir. So it's my great pleasure and to be here. And so thank you for this very kind introduction. I'll share now my screen and start my talk. So I guess that. And do you see that? Do you see the screen now?
Yes, it's perfect.
Yes,
thank you. Okay, so I'm going to talk about how you can use quantum computers to solve some lattice gauge theory problems. I see that the title is misspelled. It's a bad beginning. Anyway, so this work has been done together with Marie-Carmen Banyuls and Sylvie Lu, who are at the Max Planck Institute of Quantum Optics. And along the way, I will mention some of the results that resulted from some long-standing collaboration with Eres Soar, who was a postdoc also at MPQ in our institute, and now he's in Jerusalem. Okay, so I think that everybody has seen this image where it has been claimed that a quantum computer has solved a task that you cannot solve, or that you cannot solve so efficiently with a classical computer. And of course, it has triggered a lot of work and a lot of speculations. But I think that there are many people already were expecting something like that. So for a long time, people have been looking at application of these so-called near-term devices, or NISQ devices for quantum computers. And in fact, I mean, this quantum computer announced by Google is not the only one. So there are many platforms where people are building these small quantum computers, or this kind of prototypes of quantum computers. So here are some examples. Some of them are very advanced, some of them are very advanced. And it's not only these NISQ quantum computers that have been built, but also analog quantum computers. So for example, in the case of cold atoms in optical lattices, then people have been able to simulate condensed matter physics problems or many body problems in an analog way. And that's also, I would say, it's a very interesting topic for looking at applications. So that's why people have been looking at applications, in particular in this kind of devices. And maybe the most direct application for these devices or analog quantum computers is quantum simulation, namely to use them in order to solve problems in many body physics. This includes ranges from quantum chemistry to condensed matter physics to high energy physics, and lately even black hole physics. And the reason why quantum computer can help, or this kind of quantum computer simulators can help a lot, I think that it's very clear, and it was already said many times, in particular by Richard Feynman in this visionary paper of the beginning of the 80s, in which he showed that if you have, in general, many body systems, and in that case, he was talking about actually high energy physics theories, then if you try to solve it with a classical computer, then you will run into some bottlenecks. So in particular, you naturally will discretize space and time. So at the end, you will have to solve some lattice problem. And if you just take a quantum system on a lattice that would describe your system, the problem that you want to solve. Then even if you take the simplest system, this would be two-level systems like qubits, or what we call qubits, then the general state of a qubit would be a linear superposition of all possible configurations. And since the number of configurations scale exponentially with the number of qubits, then if you want to solve the problem exactly, then you will have to compute all these coefficients in order to describe or to give the solution to the problem. And since there are, let's say 2 to the n coefficients, then you will require an exponential memory. So a memory that grows exponentially with the size of the system, with the number of qubits that you have in your system. But also it will require an exponential time, because you will be able to, you will have to do at least one computation in order to compute each of the coefficients. And since there are 2 to the power n, so then there will be also an exponential growth with the size of your system, with the number of qubits over the lattice sites that you make. And in fact, I mean, the situation, it's worse than that, because this is bad both in memory and in time. And if you want to trade one by the other one, so like, for example, you say, well, imagine that I have a memory that is limited. So for example, it only grows polynomially with the size of my system, with the number of qubits of my system. Then it turns out that with a classical computer, then the computational time would be like, I mean, 2 to the power n to the power n. So it would be super exponential in that sense. Now, in that same paper, he proposed, or he was saying that actually we want to try to solve these quantum many-body problems with classical computer. That's something that is not natural, because you will have to use these resources, whereas you could use a quantum system in order to solve this problem. In that case, I mean, he was describing a quantum computer, also discretized in space, and putting a qubit in each of the lattice sites. Then actually you could store the state of the system that you want to study, like in n qubits. So you want to just store the state of n qubits, you need n qubits for that. So the memory of this quantum computer will only grow linearly with the number of qubits that you want to store, yes, obviously. And so for the time, then it turns out that for some cases, we know that it scales much better than classical, with classical systems. So there are exponential scalings, exponential speed ups. And even if it would scale exponentially with n, if you want to solve some problems, it still scales exponentially with n. So we still gain in memory. So therefore, there is a big advantage in using quantum computers for solving quantum many-body problems. And so my talk is about that. So how to solve these kind of problems. And in particular, so I will give some algorithms to solve those problems. Some of these algorithms would be exponentially better than classical algorithms. So there will be an exponential speed up. So there would be something that, for example, the computational time only grows polynomially with the size of the system, where in a classical computer, it grows exponential with the size of the system. Then I will emphasize the fact that these algorithms are relatively simple, so could run in niche devices, but also in analog quantum computers, or the ones that people are building in experiments. And I will concentrate on high energy physics problems. In principle, these algorithms that I'm introducing here were developed for quantum many-body problems in general, but I will, just explain it in the context of high energy physics problems. So let me talk about a little bit, very briefly, about lattice gauge theories. And so these are the kind of problems that we want to address with the algorithms that I'm going to introduce. And lattice gauge theory is a very old theory, and typically in the language of high energy physics is written in terms of path integrals. For quantum computers, somehow, or for these analog quantum computers, it's better to write it in terms of the Hamiltonian formulation, and also to put them on a lattice. And for that, it's very useful to use the Coagut-Sascon formulation, in which now you have matter that's represented here by some fermionic modes that live in the vertices of your lattice. And you have a gauge field that lives in the links of your lattice. And now the whole state is described in terms of some Hamiltonian that includes some Hamiltonian for the matter that acts only on the vertices, one Hamiltonian for the field. These are, for example, in 2-dimension, these plaquette terms that make interaction between these 4 bosonic modes. And then the interaction between the matter and the field. And so this corresponds, for example, to some fermions hopping from one side to the next side and interacting with the gauge bosons that are in the middle. And actually, it turns out that this formulation is, equivalent to the formulation that people use normally in lattice gauge theories. You have also some gauge groups. This is represented in terms of the symmetry of your Hamiltonian, etc., etc. So the formulation is the same. It's in a lattice, but you write Hamiltonians instead of actions. Okay, so one thing that, it's important to notice is that if you want to put these problems in quantum computers, then you will have to deal with fermionic and bosonic degrees of freedom. So you have to do something with them. And in particular, for the fermionic degrees of freedom, you can always use some kind of transformation in order to deal instead with fermions with bosons or with spins. And in particular, in this paper here, we introduce a unitary transformation which has the following properties. If you apply this unitary transformation to your Hamiltonian, then you will not change the spectrum of the Hamiltonian. You will have the same properties, but it turns out that you get rid of the fermions. So at the end, the Hamiltonian that you get at this transformation, it also contains 3 terms. It's still local, like the one that you had before, but you have replaced now the fermions by qubits, so by, let's say, spins. And so what it means in practice is that, the fact that you deal with fermions doesn't matter in terms of quantum computation, because if you do this transformation, at the end you will have a Hamiltonian written in terms of spins and bosons. So the second thing that you have to do is to truncate the space of your gauge field. So typically it lives in an infinite dimensional Hilbert space. So you can truncate. There are many techniques from that. So altogether, this means that in practice, all these problems can be written in terms of some lattice in which there are basically spins or qubits in your lattice, and a Hamiltonian that is local, that is acting on plaquettes or maybe on some crosses in any dimensions. So, let's say you could abstract it and say that what you have is a set of spins that are interacting with each other. So, summarizing, you have problems in lattice gauge theory. You can reformulate the same problem, even if there are fermions, into a spin lattice in which you have qubits or maybe higher dimensional systems that are interacting with each other according to some local interactions, so interactions that act only on some regions around each of the qubits. This works in any dimensions, and maybe mention that in the case that you want to run algorithms not in a quantum computer, but in a analog quantum simulator, then this step that I mentioned of transforming the fermions into spins by some unitary transformation, actually you don't need to do that, because in some of these quantum simulators, analog quantum computers, the fermions are present there. So for example, you have atoms in optical lattices, you can choose fermionic atoms, and therefore you don't have to care about the fact that they are fermions, because they are naturally there. Okay, and so the typical questions that we want to solve in these problems is questions about the dynamics. So what happens if I start with some configuration of my matter bosonic field and I let it evolve? Or sometimes you're interested in thermal equilibrium. So what happens if I have my system at certain temperature? What will be the physical properties? Or it could be even at 0 temperature. Yeah, so that are the questions that one deals in this kind of system. So now I'm going to specify a little bit more precisely the problems that I want to address with these quantum algorithms that I'm going to mention. And for that, so again, so we have a lattice system and we have a Hamiltonian. This Hamiltonian is local. And now what you can take is, and let's assume that we have qubits. But you could, you can argue also with any system that you have, and even you could argue with fermions. The same thing applies. So the first thing is that, you look at your Hamiltonian, then we can look at the spectrum of the Hamiltonian and just draw the spectrum here as a function of the energy. And so what we will have, since we have a finite system, we'll have a series of eigenvalues of your Hamiltonian. So for example, you have n qubits, then you will have 2 to the n states that will appear here. Now the fact that this Hamiltonian is local makes the spectrum very spatial. You can see it already here, that most of the eigenstates are in the center of the spectrum, and there are very fewer and fewer and fewer on the sides. In particular, the state that has the lowest energy is the ground state. This is the one that corresponds to 0 temperature. So if we are interested in studying 0 temperature, then we are interested in the properties of this eigenstate corresponding to the energy, the minimum energy in your spectrum. And for example, if you take any other energy here, and if you go to the center of the spectrum, then, I mean, this basically, there are many states there. And if you look at certain properties, then they will look very much like random because there are so many states there. So you move a little bit, the state can change a lot. Okay, so now let's talk about the density of states. So I told you before that most of the states are in the center of the spectrum. So now what you can do is to take some energy intervals and count how many states are in each interval. And then you plot how many, I mean, you plot this number as a function of the energy. So you can make a coarse grain description, and then you will have a plot like that. And so we call this the density of states. And so in the case that I just gave you, this example here, you do this, I mean, you will get a curve that looks something like a Gaussian. And now if we include more particles, if you increase the size of the system, for example, you go to n equal 15, then you see that, of course, there are now 2 to the 15 states. So it will be there will be many eigenstates. And now you look at the density of states, it will look something like that. And what's important is that if we have local Hamiltonians, then the width of this distribution is very easy to show that it goes like square root of n. Okay, that's because we have some local Hamiltonian, then the spectrum is not completely random, but it's centered around the center with a width which runs like square root of n. And this will be important for the things that I will tell you later on. If you want to solve local problems, you have to take this into account. Actually, since we are talking about the energy, we know that the energy is an extensive quantity. So the energy, if you have a local Hamiltonian, grows linearly with the size of the system. So this is why it's, I mean, it will be useful to talk about the energy density. So we take the energy we are interested in, and we divide by the number of particles, that's the energy density. And now, if we plot the density of states in terms of the energy density, not the energy, then we see that if we are increasing the number of particles, then this curve will get narrower and narrower because we are basically, we had before that the width was the square root of n. Now we divide by n in energy. So this means that now this will get narrow. The spectrum will run from some value to some value, independent of n, so from -1 to 1, if you normalize the Hamiltonian properly. And as you see, is that most of the states, we go towards the thermodynamic limit, meaning increasing, all the states are at the center. And this actually is, it turns out that this is an exponential tail, so one can show that this increases kind of exponentially. So there are very few states here out of all the possible states. And this will be related to the difficulty somehow of solving this problem. So if I want to look at certain energy, I look at those states. Actually, there are very few states. We start doing something random with these states, it will be hard that I land there. Whereas if I'm interested at, let's say, in the center of the spectrum, so I mean, this energy that corresponds to the center of the spectrum, if I take random states, and I will be very likely be here. So these are easy to describe. So then later on, of course, I will mention that, of course, if you go to certain temperature, which are not at the center, then this problem is typically exponentially difficult with classical computers. And as I will also mention, also with quantum computers to some extent. Okay, so now with this general knowledge of physics, I would say in general, we can formulate one of the problems that I want to address here. So is you fix the energy density. So you give me the energy per lattice size, let's say. You take some observables. So this could be some observables. For example, lattice gauge theory, this could be some Wilson loop with some radius. You fix this observable. And then you would be interested in computing what is the expectation value of the observable in an energy eigenstate corresponding to this energy. Corresponding means the following. So this is an energy density. So the total energy, so the eigenstate, I will have to multiply this by n. So this is what is written here. So I'll have to take an eigenstate that has n times this energy and compute this observable there. But of course, this problem formulated like that is a little bit ill-defined because it may happen that if I take some energy density, I multiply by n. Since this is a discrete spectrum, then there is no energy there, eigenstate there. So I have to give a little width to that. So the goal would be then to take an energy, which is around this n times e with some width delta that will be prescribed, this delta. And I would like to compute this quantity with some prescribed precision, epsilon. course, the norm of this operator has to be normalized to 1, etc., etc. There are some little details, but this tells you what is the problem that I want to address. Somebody gives me some energy density, then I take the total energy, I take an eigenstate that is around it, it's in a let's say in a width delta around it, which is also given, and then I would like to compute this expectation value for this eigenstate that it's somewhere there with a precision epsilon, and I would like to know what is the computational time that it requires to do that with a classical or a quantum computer. And I'm interested in how this computational time scales with n, the total number of qubits, and also in particular with this prescribed precision epsilon and this width delta here. Okay, so the first problem is what I would call now microcanonical distribution. You fix an energy and then you would like to find what are the expectation values of observable at this energy. Okay, so the problem 2 now it's related, it's very similar. Now I have a thermal equilibrium. So I have now a Gibbs state. So this corresponds to my in the Hamiltonian and some temperature. My density operator is described by this formula. We'll see it's a normalization constant. And so I would like to compute physical properties of this finite temperature state. So as you see, what happens now is that we have this density of states as we had before. Now there is a probability of having each of the states which decreases exponentially. And actually, this is the meaning of this Gibbs state. So we want to compute an average quantity of the properties of each of these eigenstates, weighted with a probability that decreases exponentially with it. Okay, so now we can also formulate this problem a little bit more precisely. I fix the temperature, I take an observable like before, and I would like to compute this expectation value of my observable with this state, which is defined in this way, given this temperature and given the Hamiltonian, with some prescribed precision epsilon. And I'm interested in knowing what is the computational effort that I have to do in order to do that. Namely, what is the computational time and how it scales with n, the number of particles that I have, the number of qubits, or the volume of my lattice, epsilon, the error that I make, and the temperature. Okay, so these are the problems that I want to solve. Okay, so before, looking at quantum algorithms, let me say a couple of things about classical algorithms. Of course, these problems appear in physics everywhere, so they're great classical algorithms to solve some of these problems in some particular ways. You can do perturbation theory, you can do exact diagonalization, you can do tensor networks. Let me explain just one method and what is the problem of that method. And that's a method that actually is very powerful whenever it works, but sometimes it doesn't work. And that's Monte Carlo and quantum Monte Carlo. So I know that people in lattice gauge theory use Monte Carlo methods, not in the way that I'm going to explain it here, but because I'm using the Hamiltonian formulation, but it's related to what they do. And so the idea of the Monte Carlo method is the following. So imagine that I want to compute the canonical ensemble, so the Gibbs state, like before. I want to compute the expectation values of some observable. And let me take just the simplest case in which this observable is diagonal in some particular basis, okay, that I call n. So this could be, for example, just a product basis, the simplest basis that you can imagine. Then you can write this expectation value, you can write it in this orthonormal basis. And so this will be just some number. This is just the expectation value of O in this n. This is an eigenstate or the eigenstate of O in n. And then you get this formula that it's very simple. And so we can rewrite this formula as some P of n. This is this number here, which is positive, times On divided by the sum of P of n. So you immediately see that this is like an expectation value of O with a probability distribution that is proportional by this Pn. So the basic idea, in order to compute this expectation value with Monte Carlo, is just to sample this probability distribution. You have samples corresponding to different configuration to these n's that you sample according to a probability P of n. Then you compute for each of the samples the value of On, and at the end you average. And then we know very well that the error of these averages decreases like the variance of the observable that you're looking divided by the square root of the number of samples that you do. So this converges very well. And so what is the problem? Well, the problem in Monte Carlo, typically you want to do that, is how to compute this quantity, how to compute the probability. If you want to sample according to some probability, you should be able to compute this probability for each of the configurations. And this is a many-body computation. So, I mean, this is, of course, is a configuration, is an n-qubit configuration. That's an n-qubit Hamiltonian. So computing that requires an exponential effort if you want to do it exactly. That's why people who use Monte Carlo have developed some tricks in order to compute that. And one possible trick is that maybe you can just write this exponential in terms of some trotterization, or you can expand in Taylor series and put identities and you do these tricks. And at the end, it turns out that for some problems, you can write this P of n as a sum with respect now to many other configurations. So configuration n1, configuration n2, configuration n3 of some quantities that depend on these configurations. And it turns out that these quantities are always positive. Then you can interpret now all these Qs as some probabilities for this other configuration. So what it means is that you indeed can sample, you can replace it in this formula, and then you can compute this potential value by sampling not only this n, but now like many copies of your system. And if you do that, I mean, this converges in the same way. And if this happens, then Monte Carlo works very well and is able to solve very difficult many-body problems very well. Now, so the catch is that, of course, for that, you have to be able to write this P of n in this particular way, to write it as a sum of something that are positive quantities and that each of these quantities can be efficiently computed. And this is not possible in practice in many problems. And well, this is what I told you before, that if this works, then the computational time will increase like 1 divided by the error square and so on. So that everything works very well. And the problem in practice is that is what is called sign problems. That sometimes if you try to do that, then these Qs are not positive anymore. You do it with any Hamiltonian, then this will be generically not positive. And therefore, if you start trying to sample, then this will not work. You can use some tricks, but then you get an exponential problem. So whenever this is not possible, then you get an exponential computational time with Monte Carlo. Okay, so I mean, I'm saying that because one of the algorithms will get rid of this sign problem. So it will take any Hamiltonian and will be able to find, so I mean, the algorithm will be a Monte Carlo algorithm with a classical computer in which the quantum computer will be used just to compute this quantity here without the sign problem, because this will be done by the quantum computer. You will not have to do this decomposition, even if it does not exist, and therefore it overcomes the sign problem. Okay, but in order to get there, let me just talk about some quantum algorithms that exist now, not for the purposes of the problems that I want to solve, but for other problems that are equally or more important. And I wanted just to mention that there are some algorithms, and the algorithms that I'm going to propose and explain, actually, parts of them are based on some of these algorithms. And so this is why I'm explaining them here. Okay, so now we have the same problem as before. I mean, many-body problem. We have a Hamiltonian, and we want to compute properties of the system now with a quantum computer or a quantum simulator. And so what can we do? Well, the first problem is, imagine that I want to compute now some expectation value of an observable for some state that is evolved according to the Hamiltonian that you gave me for certain time. So you give me some state, for example, some product state that it's easy to prepare, and I would like to evolve my system and compute some expectation value with some prescribed precision. Actually, then it turns out that we know already for many years that this can be done efficiently with a quantum computer, namely that the computational time scales only polynomially with the size of the system. The first who realized that was Seth Lloyd in this paper here, that it showed that for these local problems and even more general problems, then the time grows polynomially with n. And the basic idea is to use a trotterization. So this Hamiltonian, that is this exponential of the Hamiltonian, then you can rewrite in terms of small time steps that you repeat many times. And then each of these time scales, you can decompose it into 2-qubit gates. And if you do that, then you get that the computational time for this kind of local Hamiltonians will scale like the number of qubits times, I mean, basically this is the operator norm of your local Hamiltonian times the time you want to simulate, square divided by epsilon, which is the prescribed error. In fact, I mean, with time, people have improved that. And now, as far as I know, there is a better algorithm that only the computational time only scale like nt in one and log divided by 1 over epsilon. So there exists a very, very efficient way of doing a simulation with a quantum computer of the dynamics of a system. And there is an exponential speed up with respect to the best classical algorithm, because as I mentioned at the beginning, you want to do something with a solve the problem exactly, then you will have to run with this exponential problem with memory and time with a classical system. And basically there are not methods that allow you to solve this problem, except for some particular situation, if this Hamiltonian is exactly solvable, or if this Hamiltonian is Gaussian, and so on. So only a few of them. On the other hand, you have an analog quantum computer, like the ones based on trap ions, atoms in optical lattice and so on, then in fact, then what you do is that you tune the interactions of your system such that they obey the laws dictated by your Hamiltonian, and then you let it evolve. So a quantum analog simulator will do that without totalization, and then it will be very efficient. This is why, I mean, for many years, we believe that a quantum computer, where this is extremely useful, is in computing dynamics of many body systems, because, I mean, it takes polynomial time, even linear in the size of the system and linear in the time. However, with a classical computer, the best methods, all of them take an exponential time. Okay, so what about the ground state? So imagine that now you don't want to compute the dynamics, but you would like to compute the expectation value of some observable now in the ground state of your system. Actually, we know that this problem is very difficult. Actually, it's QMA hard, basically meaning that even in a quantum computer, it would take an exponential time. And so this was shown that this problem belongs to this complexity class many years ago. So that's a very difficult problem. And in fact, even if it's exponential in time, may be even better still than classical, in the sense that with classical, as I told you before, you want to trade, because you have also an exponential growth in the memory, you want to trade memory by time, then it will, I mean, the computational time will run like 2 to the n to some polynomial of n's, like, and this is just an example. So 2 to the n is much better than that. So even in that case, you may gain with respect to a classical computer, if you take into account memory. However, I mean, this is not so efficient. This is exponential, and we understand very well why this is not the case. There are also some other heuristic methods that are now very fashionable, based on adiabatic, variational, and there are many of them that for which you cannot prove that they work, but maybe you tried it for some particular Hamiltonians and they work, and they're very popular for these devices because some of them you can try them right away. Okay, so this was like the introduction to the quantum algorithms, and now I move on now to the problems that I was defining before. This is not to the ground state energy, but for some energy. Now you fix the energy and you would like to compute some expectation value. And the first thing that you notice that this problem that I mentioned at the beginning, the computational time in general will be exponential. And the reason for that is because the ground state energy is included in this problem in the way that I define. So if I choose the energy to be the ground state energy, then in particular for this particular one, then we are back in the finding a problem that's in QMA hard. So somehow it will depend on the temperature. So it will depend on the energy. If we take energies that are in the center of the spectrum, of course, we know that this will work very well. And if we go to a zero, but at some point it will be exponential. This is also much less studied. So there are very few algorithms to study finite temperatures. There is a quantum Monte Carlo version, and there are some other ones that prepare some states, but all of those are exponential. And so I'm interested here in some polynomial algorithm that maybe doesn't go all the way to zero temperature, but it goes very well, very much to low temperatures, and that's still polynomial, and also algorithms that will be based on Monte Carlo, but that can be that circumvent the sign problem that I mentioned before. Okay, so this is what I'm going to show now. So first of all, I'll do two kinds of algorithms. The one will be without sampling. and will allow you to solve the problem, the first problem that I mentioned before, microcanonical values. And this is probably efficient. So I will tell you that properly formulated, you can, it's the computational time scales only polynomially with the number of qubits and so on. And so what you will have to do for this one, actually, is in order to compute finite temperature properties, you will have to use the algorithm for the dynamics that I told you before, the one that is efficient several times and do many, many measurements. And out of that, then you will be able to solve this problem. So it relies on the possibility of quantum computers on doing quantum evolution, of simulating the dynamics efficiently. The second one will be with sampling. This is what I mentioned before. It will allow you to solve problems, microcanonical and canonical ensemble problems, and a voice design problem. And here, what you will have to do in practice in this algorithm, you want to run it, is to simulate the evolution, also do the dynamics, but now the time for which you have to simulate evolution will be independent of the size of your system. I will explain that better. But the price that you will have to pay is that you will have to do many measurements, because apart from the measurements that you have to do in the first algorithm, then you will be many measurements because you will be sampling. You will be doing some kind of Monte Carlo. And one property that both of them have is that they can be applied to NISQ and analog quantum simulators because they can tolerate some errors. And I'll show you some ideas why this is like that. Okay, so I go first to the first quantum algorithm for the microcanonical ensemble. And again, so this is the problem now, physical problem number one, represented this particular way. You have Hamiltonian, you don't know what is the density of state, somebody gives you some energy here, and then you would like to find the physical expectation values of observables at this energy here. And you already see that, because the problem is that there are very few states here, and if you increase further and further and further, and this will get narrower, 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 and then there will be just, I mean, typically polynomial number of states, whereas there is an exponential number of states altogether. So these are difficult to find, at least if you do things randomly. Okay, so what would be let me explain you the idea of this algorithm. Okay, so the first idea is that you will have to prepare some state around the energy that you're interested. So this only works if you're able to prepare a state around the energy that you are interested in, the energy that somebody's asking you. So somebody gave you this small energy E, and then you compute the extensive energy E, which is the small e times n. This energy is here, and then you will have to prepare some state with this energy. Typically, the state could be a product state, and as I will mention, I mean, with product states, this works for a very big range of energies. And however, what happens is that these states will have a variance which will be very large. And so, of course, if you compute properties here, then you will not get any interesting result. So, as I mentioned before, we are interested actually in now some narrow range of energies. So we would like to have some state that actually is around this energy interval. So what we will do then is to apply some spectral filter, something that is well known in optics, for example, and just to filter out this state and to make it narrower and narrower and narrower, like it's this here. And once is of the order of the prescribed delta, then we will have the state, and in principle we could measure the observable with a quantum computer, but actually we will not do that. So because we'll see this state will be very entangled and will be very prone to errors. Instead of preparing this state, we will use a trick. We will never create this state, but we will do something different than creating the state and do many, many, many measurements. And we will show that the results of doing these measurements without preparing the state is equivalent, yes, as if I had prepared the state and they made the measurements in the state. Okay, so the idea is not to prepare the state. Okay, so now go through the steps. Okay, so the first one takes a state that is easy to prepare. For example, a product state. So if there is a product state around this energy, just prepare a product state here with this energy, which has this expectation value of the energy. And one can easily show that if you have a product state, that actually the variance will be very big. So it scales like a square root of n, the variance of a product state. Okay, so one can easily show that this is possible for some intensive energy. Okay, so for some energies that scale like n, there always exists a product state with that energy. Of course, not all the way to the end of the spectrum, not for the ground state. And this is the restriction that I told you before, that our algorithm doesn't allow you to do it for the ground state, because you should be able to prepare the ground state. And this is difficult, this is QMA hard. But if you can prepare a state of this energy, then you can do that. And in particular, I mean, one can prove that if the energy, this intensive energy is larger than some minimum value, there always exists a product state. Okay? And if your energy is lower, so your energy, you cannot reach it with a product state, we can still use an adiabatic algorithm or any other algorithm that tries to prepare the ground state and fails, but it gets closer, then you could use that one for this purpose. So this again gives you a restriction to the algorithm, because the restriction has to be that there should exist some state that you can easily prepare, for example, a product state at that energy. And this also circumvents the problem of QMA hardness of this. Okay, so the question here is that, of course, if I give you a product state and then it has the right energy, but it doesn't have the right physical properties, because if I compute expectation values of observables with product state, then, for example, it will have no correlation. So you take an expectation value of the product of two operators on two different sides, this will be a product, there are no correlations, so that's not good enough. That's why we want to have some delta that is smaller. We want to make this narrower and narrower and narrower and approximate, let's say, what would be the microcanonical ensemble, which you will recover physical properties that you're interested in. So this is why you apply this filter that I told you before. And so the idea is to apply a filter, which mathematically means that you take your state you started with and you apply some operator. And this operator will depend on the Hamiltonian and on delta. So we will just filter the states that are around some energy. And so we will use this Gaussian filter. So this is described here. So it takes your energy, is zero in this case, or E, and has a Gaussian functional dependence of your Hamiltonian. That's an operator that if you act on your state, then you can see that indeed it will filter that and it will have a width at the end of your state, which is of the order of this delta, which depends on, it's defined by your filter. And now what you can do is that you can write, like we do in optics also, you can write this filter as a discrete Fourier transform. So you can approximate now this Gaussian with a Fourier transform. And then you see already here that this means that you will have here some evolution operator. So you rewrite your filter. What you see is that basically what you have to do is to apply an evolution operator to your state. And in fact, you just replace this in this formula. You see that the state that you get would be a linear superposition of evolving your state for different times with certain coefficients that you can compute classically, right? So at the end, you have to be able, if you want to do that, to prepare a superposition of your state with many different time evolutions. And I mean, this will be difficult in practice. So, however, you can circumvent this problem. You don't have to prepare the state. And the idea is to do something else that you don't have to prepare the state to get the same information as if you had the state. And that's the first step. But before that, let me remark is that, so you want to approximate this well with some, I mean, I didn't write the error here, but you see that the number of terms that you have to take here scales like a square root of n divided by delta. Okay, you want to have an error of the order of epsilon. Let's say there would be some epsilon appearing here, 1 over epsilon appearing here, but that's the scaling. It goes like a square root of n and 1 divided by delta. Of course, the narrower you want to make it, then the more, I mean, the more terms you need in the sum. This is 1 divided by delta. And on the other hand, the maximum time that you have to run your algorithm, so there will be a linear superposition. So the maximum Tm that appears here is like 1 divided by delta. That's very easy to see. Okay, but notice that, okay, this state, first of all, is not normalized. The operator that we applied, I mean, it's an operator is not unitary, so the state is not normalized. So this means that if we want to prepare the state, so first of all, this will happen only probabilistically because it's not normalized. So it may well be that the probability of getting that state is exponentially small. And also that the state is highly entangled, so it will be difficult to prepare. And that's why we have the third step. That's the one that I mentioned. And the idea is never create the state. Because at the end, what we want to do, the problem that we want to solve is to compute some expectation value with that state Okay, so what we want to do is to compute the expectation value. So like if we would measure this expectation value with that state. But what we can do is that we can replace the formula of this filter state there. And then we see just right away, without entering the details, that there will be the C, these classical computable quantities. And then what we will have to be able to compute is this quantity, starting with this P, e to the minus H, and then ended up with a P. And this quantity is the one that appears in the denominator. And also, for the numerator, something very similar, where the observable is there. So this means that actually, if I want to compute this observable, what I have to be able is to measure A and B. I don't have to prepare the state, but I have to be able to prepare my initial state, evolve it, and then look at this expectation value. And if I'm able to do these things, then I will be able to compute it. And if I'm able to do it with a small error, then I will compute the O with a small error that you can compute just very easily, how the errors accumulate and so on. And so the idea then is to measure these quantities with a quantum computer and compute the expectation value with a classical computer. And in particular, I mean, I don't want to enter into details, so that there is an algorithm that does it, and it does it efficiently. But for example, you had a classical, an analog computer, then there is a relatively simple way of measuring that. And the idea is that you can, I mean, for certain problems, for example, Hubbard problem and some problems that, that appear in these lattices, then it turns out that this quantity A of t, it's something which is the absolute value times some phase, and the phase can be computed exactly, classically, with, let's say, in polynomial time, very, very efficiently. This means that actually, for what I told you before, you just have to be able to compute the expectation value. But the expectation value squared is nothing else than the probability that you start with your state P, the product state, you evolve, and you end up with the same state. So what you can do is to start with the product state that corresponds to the energy that you want, evolve, and then check if you measure, you have the same state. And if you have the same state, you give a 1 here, and if not a 0, you repeat it many times, and then you will be able to compute this quantity A squared. With the phase, you can compute the A, and the same thing with the B, and with that, you can run your algorithm with an analog simulator. You have a quantum computer, then you can just measure this in a different way, but also efficiently, if you can, as long as you can evolve your system efficiently. But we said before that this is the dynamic problems, and the dynamic problem can be efficiently computed by a quantum computer. Okay, so summarizing, this is the algorithm which I give you some energy E and multiply by N. I'm looking here, and I want to, so you formulate it precisely, then you would like to take some delta here, and then to take a state that has a width delta and be able to compute this observable with this width delta, and to compute it with some error epsilon. The quantum algorithm is prepare a product state at that energy, evolve it for a time, which is 1 divided by delta, and measure, do it several times, and then repeat this for different time n's, this number of time n's, and then compute the expectation value. And you can check right away that the computational time with a quantum computer increases polynomially with n, with 1 over delta and epsilon. And in particular, now you can go to physics and say, what are the delta that are interesting in practice to get microcanonical ensembles? And you can see then the delta has to be of the order of 1 over n. So at the end, you have that in order to compute now things that are thermodynamically interesting, then you will have a computational time that will be polynomial in n. And if you try to solve the same problem with a classical algorithm, even if there exists a state and exactly the same problem, then as far as I know, you will take an exponential time. So there is no a better classical algorithm than the one that I mentioned before. And this is why this is an exponential speed up with respect to the best known classical algorithm. Okay, so I'm almost finished. Let me just mention the quantum algorithm. So the idea of the quantum algorithm is now that samples is just to express, now you want the same quantity, but now the expectation value, let's define some expectation value of some observable with some energy E in this particular form. We take again a filter in energy around this energy E with a width delta. And then we compute with this filter of energy the expectation value of O with each of the eigenstates. Imagine that this is the goal. Of course, when delta goes to 0, then this would converge to this microcanonical value. And in fact, I mean, you can just see that this problem is nothing else but a problem in which this quantity here can be written as is positive. So you can re-express this in terms, well, actually I have to be a little bit careful. So you can re-express this formula, just believe me, in terms of some positive quantity, some expectation value of an observable, in which this positive quantity is the one that we had before. So this means that this problem of computing expectation value with some filter function at around some energy for the filter delta actually can be computed by sampling, as long as you can compute this efficiently and as long as you can compute this quantity efficiently. But this quantity is the one that I told you before that you have to compute, basically, the one that the previous algorithm does, and this can be computed efficiently. So this means that now this problem can be solved if you can sample. You use your quantum computer to compute what is the probability of sampling. Then you sample classical configurations, the one corresponding to this piece, and you compute this expectation value also with your quantum computer if required. It can be done efficiently. So at the end, this is a Monte Carlo method in which you're using your quantum computer in order to compute these quantities that cannot be computed with a classical computer with the algorithm that I told you before. So, I mean, this is not a provable as an algorithm because, of course, the sampling, you cannot promise that the sampling will converge. In Monte Carlo, it's the same thing with classical systems. So you may have a bottleneck in Monte Carlo. So here you may find the same bottleneck. But what it does is that avoids the sign problem because you're computing this probability, these numbers, something that you can not do classically with your quantum computer. So you're using the quantum simulator as a subroutine of a classical Monte Carlo method. And okay, this requires more measurements. This, in order to get the same thermodynamic values that I mentioned before, that it turns out that it requires deltas that are smaller, of the order of 1. We'll see that in a plot in a second. And so what we did is that actually we took a problem that we can solve with a classical computer efficiently. This is an Ising model in a transverse field with n equal 20 particles, with n equal 100 qubits. And then, I mean, as I mentioned, you can solve this problem. You can use Jordan-Wigner transformation. And then we can plot, I mean, you can simulate this quantum algorithm with a classical computer. That's what we did. And so what we saw is that, because you've got, I mean, there is a phase transition here. You're above the phase transition or below the phase transition at 0 temperature. Then you see that the dot points, which are the simulation of the quantum computer and the exact solution, which are the straight lines, basically coincide. And you can do the same thing now for 100 particles, and you see that the same thing, and that you see the straight lines, the classical, the exact result. We were not able to compute it exactly with a classical computer. It got already difficult here because of precision. Of course, there are some other methods in which you could compute it. We didn't do it, but in any case, it's, I mean, it shows that it works very well. Also, that you see this is for delta equal 4 and for delta equal 1, delta equal 4 and delta equal 1. So you see that if you increase the number of particles, these delta get together. So you're getting closer to the thermodynamic limit, then it's sufficient to take delta equal 1. So that's what I mentioned, that at the end, you just require a time of the order of 1 over delta, which is 1. And also what we did here is that we put some errors by hand. So we produced some errors and we simulated that the quantum computer has errors, and that's what is described here. And this is the error that we see. So you say that these are, I mean, relatively small errors that we see as compared to the variables that we have. So we say that putting 1% error, we get something between 1 and 5% error in the results that we got. And so that's the same thing now here for the other value, for the other, I mean, inside the other side of the phase transition, but it's very similar. And to finish, then we mentioned that now actually it turns out that canonical ensemble can be also solved in the same way. I don't have time to explain it in detail, but also by sampling. And so we also did calculations and simulating with the same problem, now computing this canonical ensemble with 100 particles, and then we saw that it works very well for time. So you typically will have to do, I mean, for this kind of problems, of the order of 10 to the 7 measurements at the end, you have to run your evolution for the order of time equal 1, let's say in dimensionless units, and so this works very well. So with that brings me to the conclusion. So I have given some algorithms for finite energy and finite temperature, what I was calling microcanonical and canonical ensemble. So one of them is efficient, it's in polynomial time in order to get with some precision, let's say epsilon, the value of observables for delta of the order of 1 over n. So there is an exponential speed up with respect to the best classical algorithm. And the other one circumvents the sign problem. It's not probably, I mean, you cannot prove that it converges, but typically I guess that it will converge in practice. And they're relatively robust against noise. So this is why we think that they could be run. And actually now we are collaborating with some people who have these devices and allow quantum simulators to implement it for some particular problems. The requirement is that you have to be able to prepare states of the desired energy for the first one. And then you have to measure these quantities that I mentioned before, this probability that you end up with the same state that you started. And so as the outlook, okay, so now we are looking at more errors, and so how to, be able to work in a more reliable way, even in the presence of errors. We are adapting it to different platforms. We are looking for some other quantum algorithms using the same idea. And also we are taking now classical algorithms based on tensor networks, using this in order to compute finite temperature properties in 1 and 2 dimensions, and something for tensor networks sometimes gets a little bit difficult. And with that, I would like to thank you for your attention.
Thank you very much, Ignacio, for this really, really nice talk. Thank you so much. It was very clear and beautiful, actually, I would say. And so Simone will kindly now moderate the questions. So Simone, I pass this to you.
Thank you, Yasser, and thank you, Ignacio, for this very nice talk. So I see the first question of our public, so please write your questions in the chat and we will go one after the other. So the first one is, how do you control evolution of analog system such that its state Hamiltonian stay the same as what was used for modeling the problem? This is not an evident task. From Ziapur.
Okay, so what happens in analog simulation? That's a long answer, so I'll make a short one. I will give a short one. But the idea is that in analog quantum simulator, when you tune your parameters in such a way that your system replicates the Hamiltonian that you want to simulate, in practice, to do it with infinite precision, it's impossible. So there will be errors. So it means that in practice, your Hamiltonian in your system will not be the one that you have. But the same thing happens with the NISQ devices, so they have errors. And so the question is how these errors accumulate during the evolution. And that's something that, people have written some theoretical papers, but I think that there is a very good evidence that for the experimental evidence that for the problem that people have simulated in the lab, these errors, accumulate like one would expect. And what would expect means that these errors are extensive, so proportional to the number of particles that you have at the number of lattice sites. So the total norm of the error operator that you have, it can be very big. However, if you're looking at the end at intensive quantities, if you're interested in local observables or things like that, then it turns out that the error is this total error divided by n, so you get an epsilon, you get the intensive value of the error. Or, just roughly speaking, you have a Hamiltonian that has nearest neighbor interaction plus an error epsilon times the near neighbor interaction, then the error will be of the order of epsilon in intensive quantities.
Thank you, Ignacio. I hope that this answers the questions and why we are waiting for more. So maybe I can ask you, as you mentioned, and now you are applying this with simulating all the quantum process with tensor networks, and especially you mentioned tensor network in 2D, and you need the dynamics for that. So of course, I'm curious to ask you how.
So we wrote a paper a year ago, and Philippe Corbeau's also another one, in which we showed that in 2 dimensions you can do dynamics. The tensor networks, it's very unstable, but you can do dynamics for times of the order of 1, let's say in the typical unit, j equal 1. And so for that it's stable. Mm-hmm. But as I mentioned, for this Monte Carlo method, that's enough. in order to get the final temperature. And that's the idea. The idea is that we will have to simulate only for very short times. For that, the tensor networks methods work in higher dimensions. So we haven't done that. I mean, we're trying to do that, but in parallel, we'll do it now for 1 dimensions. And in 1 dimension, the idea is that, as you know very well, Simone, I mean, there are methods developed by you and by some other people for finite temperatures, namely for the canonical ensemble. But for the micro-canonical ensemble, that's not so easy, or at least I don't know that good methods. And this is what we can do with this method. We can look at the micro-canonical ensemble now by combining, I mean, the things that I was mentioning, Monte Carlo with tensor networks.
I see. Okay. So this probably also answer to my second question, which is when you show that you just need to compute in the quantum processor these A and B's coefficients, which, as you mentioned, are Losch-Mitico or survival probabilities. I wonder. So when you are in a many-body quantum system, those becomes exponentially small very, very quickly. So is that does that not imply that then you need an exponentially high number of measurements to evaluate them?
That's a very good point. And actually, this was the difficult part of the proof, in which we had to prove that in order to get with an error epsilon, with some n and some delta in the results, then actually it turns out that these numbers are polynomially small only. So that there is, meaning that there will be one of them, or the sum of all of them will be only like 1 over poly n, small. So this means that this is the precision that you require. And of course, if we go, I mean, we know that if we go to long times, there is an exponential tail. But the idea is that you can stop and get the result before you get there.
And here I see another question from Domenico Pomarico. Some quantum classifiers consist in expectation values. Are the composition for Monte Carlo in your talk a classifier ensemble? Can we include entanglement among them?
Okay, so I think that I mean, I'm not able to answer this question. I don't know what a classifier is. I'm coming from the physics community. Probably this is more a computer science question, and I don't know what well, I have a rough idea of what classifier is, but I don't know how it's related to this problem. So
let's see if we have some feedback with a delay we have from YouTube, and just wait a couple of seconds. Then, meanwhile, I ask yet another question, which is, so if you are doing all that with tensor networks, then do we still need quantum computers or not? When do we will need them?
Okay, well, I mean, we are doing it in tensor networks in 2 dimensions that we are trying. And what my expectation is that if you want to go to lower temperatures and if you want to go to lower energies, then probably these tensor networks will find some bottleneck. Whenever, well, as well, you know very well also that if in 2 dimensions, if we use at least some tensor networks like PEPs, and I mean, you can compute some expectation values, but it may happen that this not work. You have to contract tensors. Contracting tensors are a sharply hard problem. And so in practice, they may not work. So nobody promises that they will work. And so that's why, I mean, it's more like a trial and error. So my guess is that for some Hamiltonians, it will work. For some Hamiltonians, it will not work. The same thing is with Monte Carlo, with some of them doesn't have the sign problem. Some of them have the sign problem. So tensor network will add up to the list of tools. But the quantum computer would also complement that for some problems for which neither tensor networks nor Monte Carlo works.
Thank you. So I don't see any other urgent questions. So I would say we can also, our time is essentially finished. We are over by a couple of minutes. So yes, sir, to you to close the session. Thank you.
Thank you very much, Simone. So thank you once again so much, Ignacio, for this very nice talk. And I would like to thank all of those who participated, not only today, but also in the previous sessions. So together with Andres Ambainis, João Seixas, and Simone Montangero, we launched this Quantep seminar, so quantum computing for high energy physics, back in October, a couple of months ago, and the response has been really overwhelming and beyond our expectations. We've had live participants from India, Middle East, across Europe and the Americas, all the way to the West Coast. So this response convinces that it's worth continuing. So we are very happy to announce that the QuantApp seminar will continue in 2021, and we already have the first few sessions scheduled. So I want to thank your participation. I want to thank again the wonderful speakers that helped us launch the seminar, and of course all the organizers. And so let me just maybe share my screen to announce the next talk, which will be by Alberto Di Meglio, who is leading the new CERN Quantum Technology Initiative, which in fact is going to be launched in January. So it will be great that we'll hear firsthand about this initiative. And exceptionally, we will not have the talk on the first Wednesday of the month because of the holidays. So exceptionally in January, it will be the second Wednesday of the month, and then we'll go back to the first Wednesday of the month for our regular schedule. And so this is it. Thank you very much. Let me also acknowledge the logistical organization by Sagar Pratapsi and Rafael Ribeiro, who helped put this online seminar together. And once again, the co-organizers, André Zambaini, João Seixas, Simone Montangero, and all our speakers, and especially today, Ignacio. Thank you very much once again. And so happy holidays, everybody, and see you next year. Thank you very much. Bye-bye.